Hello, today we are diving into one of the most important concepts in operating system, deadlock. Imagine four cars arrive at a four-way crossing at the exact same time. Each driver waits for the other to move, but no one does. The result, a complete standstill. This is exactly what happens in computer system when resources are stuck in a waiting loop. We call this situation a deadlock. In simple words, a deadlock is a state where two or more processes are blocked forever, each waiting for resources that the other holds. Necessary conditions of deadlock. First, mutual exclusion. A resource can be held by only one process at a time. Second, hold and wait. A process holds at least one resource while waiting for others. Third, no preemption. A resource cannot be forcibly taken away from a process. Fourth, circular wait. A cycle of process exists where each one waits for a resource held by the next.
In an operating system, multiple processes often compete for limited resources such as memory, CPU, cycles, files, or devices. So, deadlock basically occurs when a set of processes are blocked because each process holds a resource and is waiting for another one held by a different process. So, basically, in simple terms, it's a situation where every process in the system is waiting indefinitely and no further execution can take place. So, deadlocks are one of the most critical issues in process synchronization as they can completely halt system performance. Let's visualize this with a real world analogy. So, imagine that two people are sitting across a table. Each one of them is holding one fork and needling two forks to eat. Both are waiting for the other to put theirs down, and so both stay hungry forever. In computer terms, each process is holding one resource and waiting for another. Unless and until something interrupts or resets the system, the waiting continues endlessly. This illustrates how circular waiting causes a standstill both in real life and in computing. So now let's look at this concept technically using a resource allocation graph, which is also known as RAG. In a RAG, processes are shown as circles and resources are shown as squares. So, an arrow from a process to a resource indicates a request edge, meaning that the process is requesting that resource. An arrow from a resource to a process indicates an assignment edge, meaning that the resource is currently allocated to that process. A deadlock exists in the system if and only if the graph contains a circular chain of processes where each process is waiting for a resource held by the next one in the chain. In this diagram, here you can see that processes P1, P2, P3, and P4 are all linked in a circular dependency. Hence, the system is in deadlock. So this image here is now a more detailed representation of a deadlock cycle. Here the process P1 holds resource R1 and it is requesting R2. So then process P2 holds R2 and it requests R3. This cycle continues. So process P3 holds R3 and requests R4. And finally, process P4 holds R4 and requests R1, completing the loop. Each process is both holding one resource and waiting for another because the resources are non preemptive, meaning that they can't be forcibly taken away. So, this system now reaches a permanent state of waiting. This cycle can grow more complex in real world systems where resources include semaphores. They also include file handles, memory buffers, or even database locks. In such cases, deadlocks can bring down an entire subsystem if they're not detected at the right time and resolved.
Hello everyone. Today I am going to explain the banker's algorithm, a classic deadlock avoidance technique used in operating systems. This algorithm was developed by Edsger and is called the banker's algorithm because it works just like a banker who lends money only when he is sure that all borrowers can repay safely. Similarly, the operating system allocates resources in a way that ensures all processes can finish without leading to deadlock. In this method, we deal with a few important terms: available, max, allocation, and need matrix. The system constantly checks whether allocating resources will still leave it in a safe state. If yes, the request is granted. If not, the process must wait. The safe state means there exists a sequence in which every process can finish successfully, while an unsafe state doesn't guarantee that and may lead to deadlock. The working steps are simple. First, check if the process request is within its need and within the available resources. Then temporarily allocate resources and verify if the system remains safe. If it does, the allocation is confirmed. Otherwise, it's rolled back. The algorithm uses matrices like available, max, allocation, and need to calculate a safe sequence. For example, a valid safe sequence might be P1, P3, P0, P2. Although the banker's algorithm efficiently prevents deadlock and ensures a safe resource utilization, it has a few limitations. It requires prior knowledge of system resource needs and becomes complex for large dynamic systems. In conclusion, the banker's algorithm helps the operating system balance safely and resource allocation efficiently, keeping the system stable and deadlock free. Thank you.